Welcome to your final review for the year video. We're going to be looking at our patterns here, slightly different format, but same strategy, step-by-step equations here. If this is empty on your page, please answer this first. Answer questions, even if you haven't answered it, you need help, just get the help you need, then move through as far as you can, then use my video to check. I'm going to encourage you to pause throughout this and work ahead of me. And then use the video to check your answers, not just get the answers. All right, so to start off, we're pushing a car up a ramp, W equals. So we're going to look at our equations page and find the W, right? The work. Work equals force times distance. Force times distance. And then it asks us to take the F net equals. And it says solve algebraically for the requested variable. So we are going to take this work equals force times distance equation and algebraically get F equals. Now, if these were numbers, you would know what to do. If this were 8 equals F times 4, you would know to divide by 4. Just because they're letters doesn't mean it's different. We're going to divide both sides by D because we're trying to get F alone, right? And so F equals work over force. Work over distance. So F equals work over distance. Now it's very easy to say, okay, if work equals 20, then F equals 20 over distance, and we can put in all of our distances. So we get an inverse pattern because this is going down as we plug in our different D's, and then the crucial part is this real-world application. How can we use this pattern to help get a heavy couch into a truck? So the couch has a certain, mass, right? And we're trying to lift it up to a truck. So we have to do a certain amount of work. Now, to get that heavy couch, it's heavy, we can increase the distance to reduce the amount of force. Increase D less F, right? Increase the distance, less force. The second pattern also deals with work equals force times distance. And this time it says D equals, but it's a very similar strategy. We're going to do work equals force times distance, and then we're just going to algebra it up. Divide by what to get D by itself? Divide by F, right? So we get D equals work over force. I'm just getting you practicing the rearrangement of those variables. But in this case, F equals 5, so we're actually going to use this equation. We're going to find the work at these different distances. And all I did was plug in work equals 5 times D. These different distances, we get this. So we've got a nice linear relationship here. And the way to apply it is, how do we increase the energy of a baseball? Well, if we apply the force over a longer distance, what's that going to do? More distance, more work. And then what is work? Work is energy, which is kinetic energy. So if we give the ball more energy, then it will be going faster, right? It'll have more kinetic energy. All right, so for pattern number 3, the kinetic energy of a car, this one's very interesting. EK equals, again, we're going to look at our formula, right? We're going to find our equation sheet with EK, 1/2 mv squared, right? EK equals 1/2 mv squared. And then V equals. So this one's a little trickier. We're going to rearrange this equation until we have V equals. I want you to try it before I do this. I'm going to do it, but I want you to try it first. Seriously, I'm pausing until you try this. You pause the video. All right, so we want to get V by itself, so we're going to do things until V is alone. We're going to do things like divide by 1/2 times M. If we get rid of both of those, right, this is all gone. Dividing by 1/2 is the same as multiplying by 2, and then we divide by M. So now we have V squared equals 2EK over M, and now to get V by itself, we have to square root both sides, and so V equals the square root of 2EK over M. Now, so if M equals 1,500 kilograms, well, then we're just going to use this equation to solve EK. EK equals 1/2 times 1,500 times V squared. And we get this extremely quadratic relationship. And we kind of know it's quadratic because the v was squared, right? That's going to make a quadratic relationship. So according to this pattern, why is it so much more dangerous to go too fast in your car? Well, because more velocity makes quadratically more energy. So when we increase the velocity, the energy goes up not just linearly, but quadratically. So going twice as fast is 4 times as much energy. And when we brake, braking converts to heat energy. If we have more energy, we have more to convert to heat energy, it's going to take us much, much longer to stop. That's a crucial idea. We have so much more energy that it's harder to lose that energy again. Or, if we run into something, we have a lot more energy when we run into it. All problems all around. All right, so wavelength versus frequency. Now this is changing gears completely to energy. To wave from energy. But velocity of a wave equals, let's look at our thing. Velocity of a wave equals frequency times wavelength, right? Frequency times wavelength. And to rearrange this, we have V equals F times this, and we want to rearrange it so we get wavelength equals. Well, we just divide both sides by F, and so frequency equals velocity over, wavelength equals velocity over frequency. So velocity over 2, we need to use this time. Wavelength equals 2 over F, and we can fill these in. And we can see we get this nice inverse relationship. So what does this mean about how to create high versus low frequencies? High frequencies require what kind of wavelengths? Low wavelengths. And low frequencies require high wavelengths. And the crucial part of that is like instruments, a pipe organ. We got really small pipes create those really high sounds, and really long, huge pipes create the really low sounds.